All right, and the function we're going to do the mean value theorem on is f of x equals x cubed minus 3x plus 2 on the interval negative 2 to 2. All right, so to show that the hypotheses are fulfilled for the mean value theorem, we have to show two things: that it's continuous and differentiable on the interval. Well, since f is a polynomial, f is continuous on all real numbers, and f is differentiable on all real numbers, because that's how polynomials work. Okay, so those two things mean we can use the mean value theorem. All right, and then just like we've done in the past for our big theorems, like our squeeze theorem and our intermediate value theorem, we're going to want to say, once we show the hypotheses are satisfied by the mean value theorem, all right, so that's important. I'll be looking for that on the exam. There is a number c in the open interval negative 2 to 2, such that, or where, f prime of c is equal to the slope of that secant line between the endpoints. All right, so that's the MVT. So let's do a little scratch work off to the side. What is f of 2? Because remember, now that we showed that it fulfills the hypotheses, we have to find all of the c's. We can't find the c's unless we know what this is. So 2 cubed minus 3 times 2 plus 2, right? So 8 minus 6 is 2 plus 2 is 4. And f of negative 2, negative 2 cubed, so negative 8, minus 3 times negative 2, so positive 6, negative 8 plus 6 is negative 2, plus 2 gets us back to 0. All right, so we have to find all of the c's that satisfy this. F prime of c is equal to 4 minus 0 over 4. 2 minus negative 2 is 4. All right, so we made these substitutions. So 4 divided by 4 is 1. So this question is now, where is the derivative equal to 1? Okay, so that's where we're going. So let's figure out what the derivative is. Okay, going back to our original function, we're looking at 3x squared minus 3 plus 0. So 3x squared minus 3. And so we want to find all of these c's. So we'll plug in c. We want to figure out where that's equal to 1. All right, well, we got a quadratic, so we have two ways of solving quadratics. You can make one side 0, right? Then use the zero factor property or quadratic formula. This doesn't have that middle term, that c term, so we can also use the square root property. That's what I'm going to do. So I'm going to isolate c squared. So add 3 to both sides. And then divide by the coefficient to isolate c squared. And now the square root property says we can take the square root of both sides and add a plus or a minus. All right, so 4 over 3. Okay, and we can clean that up a bit. Square root of 4 is 2 over the square root of 3. You can leave it like that. We can also, as you know from your algebra class, rationalize your denominator. We're looking at plus or minus 2 root 3 over 3. So there you go. So the c can be those two numbers. It can be negative 2 root 3 over 3, or positive 2 root 3 over 3. We have to think of one other thing. And remember, we want the c to be a negative 2 to 2. So we can probably do that in our calculator. But let's see, this is going to be like 2 divided by 1 point something, right? So it's definitely going to fall in this range, positive and negative. And you can verify that on your calculator as well. So since both negative 2 root 3 over 3 and positive 2 root 3 over 3 are in that open interval, negative 2 to 2, that's your C's. Your C's are both of those numbers. All right, and then that's what that problem asked. They wanted us to verify that we could use the mean value theorem, and then they wanted us to find all the C's. There you go. Okay, so we're going to do, well, you guys are going to do another example. We're going to head on over to number 14. Same type of problem. You're going to verify that hypotheses of the mean value theorem hold. And then you're going to find all the numbers C that satisfy the mean value theorem. And number 14, you guys are going to push pause and you're going to do that same process on 1 over x over the interval 1 to 3. All right. So let's verify that they hold. We're looking at 1 over 3. Excuse me, on the interval 1 to 3. If you don't remember what the graph of 1 over x looks like, 1 over x looks like this. And the only time it's not continuous, the only number not in its domain is 0. X can't be 0. So if we're looking at 1 to 3, we're looking at this interval right here. And we can see, and we know that 1 over x is continuous on its domain, and 1 over x is differentiable on its domain. Because polynomial functions, or excuse me, rational functions are continuous and differentiable on their domain. All right, so there you go. We could say rational functions, are continuous and differentiable on their domain. All right, so there you go. That's that first part. So now it's time to find all C that satisfy the mean value theorem. Okay, so again, by the mean value theorem, f prime of C is going to be equal to the slope of the secant line. You can kind of sketch it out right here, 1 to 3. The slope of that line is what we have here, the difference of y's over the difference of x's. All right, and then we're saying, again, what the mean value theorem is saying is that there is a C somewhere between these points where the slope of this tangent line is the same, or the derivative is the same. So in this case, we can see we're just going to have one C. We're just going to have one C. It's going to be right there. So we're going to figure out what that number is. Okay, so let's clean this up. F of 3, if our function's 1 over x, it's going to be 1/3 minus f of 1 over 2. Okay, so 1/3 minus 1 is negative 2/3 divided by 2, or multiplied by 1/2, and then that should simplify, or it does simplify, to negative 1/3, right? We see we have this common factor of 2 in the top and the bottom. So negative 1/3. So we have to find all of the C's, all of these C's where the slope of the derivative, excuse me, the slope of the tangent is negative 1/3, which is exactly what the derivative is. All right, so let's continue. We're interested in the derivative function. I like to think of x, or our function 1 over x could be like x to the negative 1. That way it's a little bit easier to take the derivative of. So the derivative of the function is negative 1 over x squared. Okay, so we want to know all the values of c, so f of c, f prime of c, where that's equal to negative 1/3. Okay, so that's kind of nice. Let's see, a couple of things happen. Minus, minus, we can kind of cancel them. We can do a little cross multiply, if you will. And essentially this becomes that c squared is equal to 3. So we can use the square root property again. C is equal to plus or minus root 3. All right, so those are our candidates. Now we have to consider our interval, and our interval is between 1 and 3. So negative root 3 would be all the way over here. So that's not going to work. So in this case, we just have 1 positive root 3. So we have to throw out the negative sign since it's not in the interval. All right. And then that's that. So that would be the end of that problem. That C satisfies the mean value theorem. All right, good. Let's do another problem together. We're going to head on over to number 26. And this problem is interesting, and I'll just kind of preface it before I read it. So we're going to use the derivative to find out information about a function. So we will find information on a function only using its derivative. All right, and so here's the problem on number 26. It says, suppose that your derivative, f prime of x, is between 3 and 5 for all values of x. Kind of looks like a weird function, right? So if you can just picture that. We kind of have these borders for this, whoops, let's reverse that. We have these borders for this function, right? So the derivative is somewhere doing something, we don't know, but it's between 3 and 5 for all x. We're going to show, just based off the derivative, what we can show is that our function f of 8 minus f of 2 is going to be between 18 and 30, just based on the derivative. All right, so pretty powerful. All right, let's make sure I wrote everything down correctly. 3 and 5, 18 and 30. Okay, so because a derivative exists, right, f prime of x equals 5, we know, and it's true for all x, we know f has to be differentiable for all x because of that very first piece of information we're given. So f is differentiable for all x. All right, and we had a theorem that if we're differentiable, we're also continuous. So by theorem, since f is differentiable, f is continuous. It doesn't go the other way, right? Continuous functions aren't necessarily differentiable, but differentiable functions are automatically continuous. Okay, so those are the two criteria for the mean value theorem. You have to be differentiable and continuous. So we can say by the mean value theorem, by the MVT, there exists a C in AB where it's equal to the slope of that secant line. That's the MVT. All right, and we'll write for some C in AB. All right. So what should that interval be? What should the x and the y value, the x and y, sorry, the starting point and the ending point, what should the two endpoints be, the inputs? Well, let's use the inputs up here. Let's be strategic. All right, so we'll say A is 2 and B is 8. Okay, so we're going to be looking at that interval. So let's choose, it's true for any open interval, but we're going to choose 2 to 8. Okay, so that means then that f prime of c is going to be equal to f of 8 minus f of 2 over 8 minus 2, which is 6, so I'll just write in 6. All right, lovely. And then what do we know about the derivative? Well, the very first thing they said, or what the only thing really we're assuming, since our derivative is always between 3 and 5 for all x, that has to be true for c as well. Okay, so let's put this, which is also f prime of c, we'll put it in the middle. So a little substitution. All right, and then we're almost done. Let's get rid of this denominator. We can multiply 1, 2, 3 parts by 6. And then that's actually what we were trying to show. That's exactly what we were trying to show. So we're done. Okay, so just given this little piece of information, we were able to prove that f of 8 minus f of 2 was between 18 and 30. All right. So let's move along. We're going to look at a couple little theorems, and then we're going to use these little theorems to prove little statements. So here's our first theorem. If the derivative is 0 for all x in an interval, so no change over this whole interval, f of a to f of, or a to b. Well, if there's no change, what does that say about the function we have? Then f is constant. That's the only time we would get no change is if we are a constant function. All right, so a to b. We can also think of this as the derivative, the slope of the tangent line. I keep saying that. The slope of the tangent line is 0. Well, that means we have a horizontal line. We know that. But if we have a horizontal line over the entire interval, we have to be a constant function. All right, and then outside the interval, we don't know what happens. We don't care. We're just focused on a to b. But f has to be a constant function. All right, kind of a straightforward concept or idea. Very visual proof. So we have a corollary, and a corollary is something that happens directly from the theorem. No outside things are really necessary, and it goes like this. So it's kind of just like a corollary is a direct result from the theorem. So if two derivatives are equal, so two functions have the same rate of change for all x over an interval. For all x, remember this symbol means n, a, b, then f minus g is a constant. Over that interval. Another way of saying that f minus g is a constant, another way of saying that is f and g differ by a constant. F and g differ by a constant. So maybe f and g are the same function, they just differ by a constant. Okay, so just some examples of functions that differ by constants just to kind of get a visual in your head while we're proving this. Parallel lines have the same slope but differ by a constant. So it's really just a vertical shift, right? When we add c to the same function, it's a vertical shift. So we can have a parabola and then do a vertical shift. Those two functions would differ by a constant, okay? But their derivatives are the same. The function is changing at the same rate. It just is going up and down physically on the graph. Okay, so let's see what we can do. So let's say we define a big F. We're just going to show how we can kind of prove this really quick. We can define F to be the difference between the functions. And we're going to show that F is a constant, okay? And how we're going to do that, we're going to take the derivative of F. So we can take the derivative of the parts. And we're assuming the derivatives are the same, right? So same minus same is 0, right? Like 5 minus 5. So this whole thing is equal to 0. So we have a derivative, f prime of x is equal to 0. And that little theorem we just had said what? If the derivative is 0, then f is a constant. So this big F is a constant. All right, and then that means f minus g is a constant. That's what we were trying to show. All right, so it's a corollary. It's a direct result from that previous theorem. All right, what can we do with this? We're going to be able to prove identities with this. And we're going to go over to number 34, and we're going to see how to do that. So an application of this is we can prove identities. Okay, so number 34 says we're going to use the method that I'm going to show you to prove the identity to arc sine or inverse sine of x is equal to inverse cosine or arc cosine of 1 minus 2x squared for x greater than or equal to 0. Okay. So we're going to prove this. We can also prove as an equivalent statement to prove is if we subtract the inverse cosine from both sides, we can also prove this. And that's what we're going to focus on. It's an equivalent statement, and or an equivalent identity rather. Okay, so we're going to prove that. So what we're going to do, this is our strategy, using that little corollary from before. We're going to call this function f, and we're going to show f is constant. By showing the derivative is 0. Okay, so that's our tricky way of proving this difficult identity. Otherwise, this identity would be very difficult to prove. But we're going to show first that statement on the left is constant by showing its derivative is 0. Okay, so let's start. We're going to start by taking that derivative. So let's take the derivative of the left-hand side. Again, formally, let's let f of x be equal to the inverse sine, or whatever, 2 inverse sine of x minus the inverse cosine of 1 minus 2x squared. And now we take the derivative. Okay, so the derivative of the inverse sine is 1 over the square root. And then we have to use the chain rule here. So the derivative of the inverse cosine, oops, is negative. Put it in parentheses to protect the negative. And then it's over 1 minus x squared. But the input is this. All right, so that's the derivative of the outside function. Then we have to take the derivative of the inside function. It's going to be negative 4x. The derivative of 1 minus 2x squared is negative 4x. All right, and of course we have to clean everything up a little bit. Minus minus becomes plus. Oh, but then we have another negative sign. So let's see, 1, 2, 3 negative signs means the whole thing stays negative. 4x on the top. I'm going to expand this out in the radicand. So 1 minus 4x squared plus 4x to the fourth. All right, so let's see. I'm going to kind of do a little side work right there. So we have 1 minus 1 plus 4x squared minus 4x to the fourth, right? Getting rid of the parentheses. That goes away. So we have 4x squared minus 4x to the fourth. I'm going to factor this just because we're taking the square root. I see that there's a perfect square in there. I can factor out a 4x squared. Okay, and then when we eventually take the square root, I can separate out that 4x squared. All right, and then we're just left with 1 minus x squared. All right, and remember 1 minus x squared isn't a perfect square because it factors as 1 plus x, 1 minus x. That's not a perfect square. Okay, so here we go. This big, ugly function. Well, it's not ugly, it's just long. But then some nice things happen. So the square root of 4x squared is going to be 2x. And then do you see what's happening? Nice things are going to cancel. Let's see, we can cancel, factor out 4x and 2x. We're left with a 2. And now we have 2 divided by square root of 1 minus x squared minus 2 divided by square root of 1 minus x squared. That's the same thing. So 2 minus 2 is 0. Denominators are the same. Okay, so we just showed that the derivative of that function is equal to 0. That's what that whole shebang was. So by theorem, f is a constant. Stop it. All right, so that was the first part. That was our strategy. We wanted to show that this was constant, and we did. Now we have to show that that constant is 0. So we're almost done. Okay, so we have to show the constant is 0. And we can do that by plugging in any value for x. If it's constant the whole way. So we can choose any x value and it's going to go to that constant. Okay, so let me remind you, let's remind ourselves, myself included. This is our function. It's a big one. And it's a constant. We're going to show that constant is 0. And remember, we're plugging in values not plugging in angles or plugging in values along the circle. So I recommend, plugging in either a 0 or 1. Those are the easier ones to deal with. And then you can figure out your angles from there. So I'm going to just plug in a 0 and see what happens. Again, we can plug in any value. So for instance, the inverse sine of 0, where is sine 0? It happens at angle 0. And the inverse cosine of 1 minus 0. So again, I'll just write it all cleaned up because inverse functions can get a little bit confusing if we're not careful. All right, so this is saying where is the angle 0? At 0. And then we're saying where is the cosine? Oh, I did that wrong. Where is the cosine 1? Well, the cosine is 1 here, right? Because this is the point 1, 0, x, y, cosine, sine. So there you go. So the constant is 0. All right, and that's what we were trying to show. So it's not just any constant now, it's 0. And then let me just kind of stick with the inverse. Let me give one more example. With the inverse, we could have also plugged in x equals 1. And we can do it just for practice because, again, inverse trig functions are just a little bit tricky to get. We always kind of have to slow down and think about it. Okay, so plugging in 1 minus 2 times 1 squared is 1 minus 2. Okay, so we have to think, where is the sine function 1? And where is the cosine function equal to negative 1? Okay, well, the sine function is 1 here. So angle pi over 2. And then the cosine function is negative 1, whoops, here. X and y, cosine, sine. Cosine is negative 1 at pi. All right, and again, 2's cancel, pi minus pi is 0. We still get 0, okay? All right, so that was a little side note, working with our function. Let's put everything together. So thus, by that little theorem, we were able to show that this function is a constant, and then we just plugged in values to figure out what that constant was, and that constant is 0. And that proves that little identity. So very fun.